Okay, so we're doing homework part B, homework 2 part B. So what we're going to want to do is we're going to use the generalized cubic equation of state, and we are going to find its roots, and we're going to do it in terms of compressibility. So first, let's write down our equation. Equals, I think it is RT VB, okay? And then minus A over V plus epsilon B, V plus sigma B. Okay, so we wrote down our equation. So we want this in terms of compressibility. So a compressible formula is going to be Z is our variable for compressible, and it's going to be PV over RT. That is going to be our compressibility. And we want this to be in terms of Z, because we want to figure out what our compressibility is first, so that we can find our volume later. Because what is known is our pressure and temperature, and we need to be given our volume. So, since compressibility is going to be between a range of 1 to like 1/3, 1/3, or 3/8, 1 and 3/8, because the critical point, what we just found, which is 3/8, and then our ideal gas ratio, which is 1. So it's going to be in between that, which is going to help us figure out our volume, and it's going to lead to less error. So let's make P over here. We want this to equal Z because we want this to just start off as Z. So what we want to do is we're going to multiply by V over RT. So multiply by V over RT. And then on this side, we want to do V over RT as well. Okay, so this is going to equal Z equals P V over RT. Okay, and then the RT's cancel out here, so you have V over V minus B. And then over here, you're just going to have A, V over RT, V plus epsilon B plus V plus sigma B. Okay. This is good. Okay. So what should we do next? Well, since we know that V, our volume, is going to be a variable that we want to find, let's take it out so we can isolate it first, right? So let's isolate this. So it's going to be Z equals Z RT over P is equal to our V. Okay, so we are going to simplify this. And when we simplify this, then we're going to substitute our V into this. So to simplify it, let's do Z equals V over V. Let's cancel that out. So that's V minus B. Oh, it's 1 minus 1 minus, and then B over V. Okay, and then let's do A over V RT. And let's take a V out of here and here, since it's both in these equations. So let's take it out of the parentheses. If we take it out of this one and this one, we're going to have V squared over 1 plus epsilon B over V over 1 plus sigma B over Z. Okay. Now let's cancel out. This is going to take out a squared, and the one on the top is going to be, so it's just going to be A over here, and then a V is just going to be in the bottom. Okay, now let's substitute our V in for it. So Z equal 1 over 1B. Okay, since V is in the bottom, we're going to flip it to the top, so it's B over P ZRT. Okay, and now let's do it over here. So RT, and then this one is going to be flipped up to the top, so that's P, and then RT is going to be at the bottom, so that's going to be squared squared. Keep that in the bottom. Okay, so now we have to do these. So it's going to be 1 plus epsilon. Okay, so where's our z's? Our z. Is it here? There's a z here. Okay, z is here. Forgot about the z. Okay, so then epsilon b, and then flip it so p comes up to the top, and then zrt, and then 1 plus sigma bp over zrt. Okay. Now, we see some common variables together. We see bp over zrt. And I think let's just make a variable for it. So I'm going to say that beta is going to equal bp over zrt. Let's use that as our variable. So we can substitute in here, here, and here. Now, let's look at this a at the top. It has p over rt, so, but it has an a instead of a b. So let's use the top as a, and then beta over b equals that. Oh, let's keep the z out because we want to isolate our z, so we want to keep our z out of that. So this is a b. Okay. And then we have another RT because we have RT squared. So we have RT. Okay. So now let's make another separate one so that A over BRT, let's make that equal to Q. Okay. Yeah, that should solve our problem for that. B cancels out so that we have, yep, okay. So now let's put in our Q and our beta to solve for this to make it easier. Okay. 1 over 1, and this is beta over z, and then this is this is going to be Q and beta over R, and this is going to be z here, okay? And now it should be just 1 plus epsilon, and then beta, and then a z, and then 1 plus sigma beta over z. Okay. This is good. Okay. So what should we do next? Well, we have z. Let's divide by c on both sides so that this z over here cancels out and becomes a 1, and that makes our life much easier. So, z over here, 1z over here. Okay, so let me erase this here, and then let's see what we can do on this side. So we're going to have 1 equals z, so 1 over z minus b, beta, actually, and then we have q over beta over, so we want to divide by z, so this becomes z squared, 1 plus epsilon beta over z, 1 plus sigma beta over z. Okay, so now we have that. Let's distribute this v into this v and this parentheses, okay? So now we have 1 equals 1 over z minus beta minus q beta. This is going to be 1 z plus epsilon b. And this is going to be z plus sigma b, beta. Okay. Okay, now we have common denominators. So let's get these out of the bottom and let's multiply by the other side. So, okay, so on the other side, before we do that actually, what we should do is we should multiply these out and get a quadratic. So this is the quadratic. So we have c squared, and then epsilon beta times c, and then we have sigma beta times c. So this is going to be epsilon plus sigma beta over beta z. And then we just have epsilon beta and sigma beta, which is going to be epsilon sigma and then beta squared. Okay. So now we multiply this and this by the other side, and let's see what we get. So we have z minus beta, and then we have z squared plus epsilon plus sigma over bz plus epsilon beta over b squared. Okay? And then on this side, I'm going to bring it down here. So then we have z squared plus epsilon plus sigma times beta z plus epsilon sigma beta squared. Okay. And then this is going to be subtract by qb times z minus b. And then let's multiply this out. So this is going to be qz, and then this one's going to be plus qb squared. Okay. Let's get our quadratic going. So it is a quadratic, so it's going to have 3 roots. So it's going to have 3 roots. So z to the third, we have z squared, we have z, and then we have just our constants, so our 1s. So multiply this by this, z times z squared is going to be 1. That coefficient is going to have 1. So z times epsilon, this one, is going to give us a z squared. So this should be epsilon plus sigma beta. Okay, so this z times this here is going to be epsilon sigma beta squared. Okay, now let's do our beta over here. So beta times z squared is going to give us negative beta here. And then this beta times this one here is going to give us a z. So it's going to be epsilon plus sigma times beta squared. And this is going to be negative because the negative on that. And beta times this is just going to give us constant of epsilon sigma beta to the third. This is good. Okay. So after we have that, let's do the other side. So the other side is just going to negate everything that we have. So this one is just going to become negative 1. And then we have this as just a z, so that's going to be negative z. So it's going to be epsilon plus sigma, and then beta. And then this one is just going to be our coefficient, which is going to be negative epsilon sigma beta squared. And then this one here is going to be a qz. And this one's going to be a positive because it's flipped on the other side. So it's going to be q beta. And then this one here is going to be just our constant, so it's going to be negative q b squared. Okay. This is us finding through our compressibility of the generalized quadratic equation. So the next, we're going to use this information here to find our roots, and then after we find our roots, we're going to be able to do the Maxwell area where we're going to find 2 sides of, that's really bad. Okay, it's going to look like this, and then we're going to find these to equal each other, and we're going to use the stuff we find here, their coefficients. Thank you. Hi, I'm doing part B 2 and 3. So it says write a function to calculate the roots of a cubic polynomial. So the first thing we want to do is in our code, let's import numpy as np. And then for our next problem, we're going to need to import. So from scipy.integrate, import quad. This is just going to calculate, help us calculate our Maxwell function. So this should be good. So after we do our imports, then we can go on to calculating our cubic roots. Okay. Okay, so now that works. So the next thing we want to do is we want to calculate our cubic equation. So to find our cubic equation, it says for this example over here that for the real or complex coefficients, A, B, and C, we need to first compute Q and R. And you can see that they have A, B, and C in there. So first we're going to define a function. And this is going to be a function to calculate our cubic roots. So cubic roots, and this is going to be based off of, dependent on A, B, and C. Okay, so next, what we're going to want to do is let's now calculate Q. And this is going to be A squared minus 3 times B. And this is going to be divided by 9. Okay, so now R is going to be 2 times A to the cubed, and then 9 times A times B plus 27 times C. This is all going to be divided by, let me put my parentheses around it. Okay, so after we calculate Q and R, let's read what it says. So it says if Q and R are real, and if R squared is less than Q cubed, then it has 3 real roots. So let's make an if statement about this. So if R square it is less than Q cubed, then what we want to do is, so if this is real, then we have to calculate our theta. So theta equals MP arctan, arc cosine, and this is going to be R divided by, and then it's going to be Q to the 1.5, because it is square root of a third, square root of a 3, so it should be that. Next, so after we calculate our theta, we're going to use this theta to calculate our 3 roots. So we wanted to return our 3 roots using these equations here. Now, if we notice, the only thing different about these 3 roots is what is in the inside of the cosine. So what we're going to do is we're going to do an MP array, and we're going to do the MP array with our cosines. But everything else is going to stay the same. So first we're going to do -2 times Q 0.5 times MP dot cosine. And now let's do MP dot array. And so we want it to go like this. So then we're going to put our first one in, which is just theta. Theta divided by 3. Our next one is going to be theta plus 2 times mp dot I divided by 3 as well. Oh, this should be subtraction. And then our second one is theta plus 2 times mp dot pi divided by 3. And then this is all subtracted by a divided by 3. Okay, so after it returns our 3 real roots, our equation says if it's real. What happens if it isn't real? What if it's an imaginary number? So let's go down here, and it says that we compute a here, our capital A. So let's go here and let's do an else statement. Else, so let's calculate a. So we're going to do negative r plus, and then we want to do the square root of r. So then inside it's going to be r squared minus q cubed. And then this is going to be 1/2, 1.5. It's going to be 0.5. So this seems right. And then we're going to have to cube, do this to the third. This is going to be to the power of the third. Okay. Next. So after we calculate our a, it says that we have to come down here. And it says that we have a b. So our b is going to be, if b is 0, then a is 0. If b equals q divided by a is not going to equal 0. So let's do a statement. So if b equals 0, if a equals 0, else b equals q divided by a. Oh, and this should be double. There shouldn't be any else in there. And there shouldn't be a b. Okay, else, then that a is also. Okay. So now what we want to do is we want to return we're going to return x1 equals a plus b minus a divided by 3. So let's write this out. Okay, let's see if this is correct. So it works, and now let's just check to see if it works. And I know that if you do negative 6, 11, and negative 6, you should get coefficients as 1, 2, and 3. Okay. Okay, so I just needed to put parentheses around the theta to fix that. Okay, so our cubic root was fixed, so it's 1, 2, and 3. Wait, okay. Reset it. Okay, so what was wrong was I needed to put the parentheses around the theta. So now the cubic root is fixed, so it's negative 1, 11, and negative 6 has a, b, and c as 1, 2, 3. So this is correct. So the next part, so we just made our function. So the next part of it, it says that using part B1, when we use the cubic state of equations for the cubic polynomial, we're going to use what we derived from there, and then we're going to use it as the SRK state of equation, and then we're going to use what we just did to calculate the roots of a polynomial, and we're going to use limits of integration so that we can find the Maxwell area. And we're going to do the estimate the vapor pressure of water, and we're going to do this at 373 Kelvin. So the first thing we want to do is we're going to put all of our initials on here. So let's first put anything that we're going to need. So we're going to need R, and then we're going to need temperature at the critical point. So water. So we're going to use the water out at the critical point. So it's going to be temperature at critical point is going to be 670.96. 96, and this is going to be Kelvin, so let's put our unit, and then we're going to have pressure at the temperature point, the critical point, and then this is going to be 222.60 kilopascals, so e to the 6. Okay. And then after that, we're going to need our W, which is 0.348. And then we're going to just have B in here because we'll need it for later. And going to be 1 divided by 8, and this is going to be times, if we go up here, it shows us that B is 1/8 times R times the pressure times R times the temperature at the critical point divided by the pressure at the critical point. Okay. So that works out. So now we want to code. So after we have our initials, the first thing we're going to need to want to do is we're going to have to do an equation for our variables. So calculate variables. So our equation, and this is going to be dependent on temperature. So we're using our SRK equation for this, so let's look at our SRK equation here. So the first thing we want to do is our temperature reduced. Temperature reduced is going to equal temperature divided by temperature at the critical point. Okay, and now we see that sigma is going to equal 1, epsilon is going to equal 0, put decimal points on them. No. And so then we're going to solve for alpha because we need to solve this. We need this to solve for our A. So our alpha equation is right here for our SRK equation. So it's going to be 1 plus, and then in parentheses, 1.8, 4.8 plus 1.54 times our W minus 1.6 W squared. And then this is going to be multiplied by 1 minus temperature reduced times 0.5. And I'll put this in parentheses as well. No, it's fine without parentheses. Okay, and then all of this is going to be to the power of 2. Okay, and so after we solve for our alpha, we need to solve for, we need to put in our omega, and then we're using the SRK equation, so. And then omega, and then we need our psi. which is going to be 0.42748. So after we find these, what we want to solve for next is going to be our A. And our A is going to be, we're going to do psi times our alpha times our R squared, and then times our temperature at the critical point squared. And I'm going to put the squared stuff in parentheses so we don't mess that one up. And then we're going to divide it by PC. Then the next one is going to be B. Our B is going to be omega times our R times our temperature at the critical point divided by our pressure at the critical point. And so after we do this, what we want to return is our variables. So our variables are going to be A, B, epsilon, and sigma. So let's calculate this. There you go. Okay, so we calculated it. Now the thing that we want to do next is we want to, after we found our variables, let's calculate let's define a function like we did in the first half, and we solved for the cubic pressure. Let's solve for the cubic pressure again, because we'll need this to solve for our areas. And this is going to be dependent on volume and temperature. So what we want to do is we're going to unpack our variables, epsilon and sigma. And this is going to be calculate. This is T. And then the next thing we want to do is we're going to return our function. And our function is going to be, we want to return our equation of state. So we're going to do this equation of state. So R times T divided by V minus B. And then this is going to be subtracting, this is going to be A divided by, this is going to be V plus epsilon times B, and then we're going to multiply this times V plus sigma times beta. No, times just B. Okay. And then let me check to see if I got this right. Okay, so double checked it, and then let's see what this does. So it gives us it. So after we calculate our cubic pressure, the next thing we want to do is we want to calculate our cubic volume. This is going to help us calculate our actual areas. So to calculate our cubic volumes, let's first make another equation. So let's define a function, and then this one's going to be cubic, and this one's going to be volume. And volume is going to be based off of pressure and temperature. So what we want to do first is we're going to unpack our A, B, epsilon, and sigma. And variables, and this can be based off of T. Okay, so we calculated our variables now. Now, the thing that we derived, this is going to help us in the first place. So what we want to do is, let's look at our beta and our Q. So we first want to solve for beta. So beta equals B times pressure divided by R divided by temperature. And then our Q is going to be A divided by, and then B times R times T. Okay, so we have our beta and our Q, and this is going to help us solve for our roots. So what we did when we derived our equation for the cubic state of equation, and we did this in respect of Z, so we found everything in here. So what we're going to do is we're going to calculate our Z. So our Z. And now we're going to do our cubic roots. So we found the cubic function. Now we're going to find the roots of this function. So we're going to use the equation that we made, or a function that we made. So cubic root, or cubic root. So the first one is going to be Z squared, then Z, and then our regular ones without Z. So the first one's going to be epsilon plus sigma times B minus 1. Okay, and then our next one is going to be epsilon times sigma times beta squared minus epsilon times epsilon plus sigma times beta squared minus plus sigma times beta, and then Q times beta. Okay, so now we got rid of the Z, so now we have to compute our next ones. So it's going to be times epsilon times sigma times beta cubed and then we're going to do minus epsilon times sigma times beta squared minus Q times beta squared. And let me fix the beta on this one. Okay, so the next thing we want to do, so after we found our Z, we know that C equals PV over nRT. And what we're trying to find is our cubic V. So what we're going to do is we're just going to resolve the equation so we solve for V. So now we're going to return that because we want to know, we didn't want to know that. So let's return Z times R times our temperature, all divided by our pressure. So this is what we want to return. Okay, so now the next thing we want to do is our Maxwell function. So let's first define our Maxwell function. And this is going to be based off of P and T, pressure and temperature. Okay, so what we want to do is we're going to unpack our cubic volume. So this is going to be PL, PM, and DG. And this is going to be unpacked, and we're going to unpack our cubic volume. And that is in respect of pressure and temperature. So next thing we want to do. So what we want to return is we want to return our two values in our two areas on both sides of the equation. So of the graph, we want the up and we want the down. and we want them to equal each other. So that is what we're going to do. And so we're going to use our quad function to find the area, and then we're going to use our cubic pressure, and then we're going to use our regular pressure, and then we're going to subtract that. And then what we just solved for with our cubic volume, that is going to help us as well. So the first thing we want to do is let's return it, because this is what we want to return. And then we're going to do our quad function, and then this is going to be our lambda. Lambda, and then V because this is volume. And so then the first thing we're going to do is we're going to do pressure, because we're on this side, we're going to be on the left side first, so the pressure is going to be bigger. So this is going to be the pressure, and we're going to subtract it by the cubic. And this is going to be based off of volume and temperature. And so this is our VL, so we're going to have VG, no, it's actually going to be our VG, so we're going to have VL and VM. And then after that, we're going to need a bracket to have our zeros. Just a 0. And then the next thing we want to do, we're going to have another quad because we need to solve for this one as well. And this one we're going to have lambda. Lambda V, and then we're going to have our cubic. So this one's going to be our cubic pressure because we're on the right side now. And so now the pressure is going to, now the volume, now our pressure is going to be below. So now we have to subtract by cubic first. So we have this, and this is going to be our VL. So we have VM and VG. Okay. And then this is going to have our bracket of 0. Okay, and so let's see if this works. Okay, so now what we wanted to do in our equation is that we wanted to calculate something that had the area close using our Maxwell to find out using a vapor pressure, and we wanted to use a temperature of 373 Kelvin. So we have our Maxwell areas, and I know that one that's really close for vapor pressure is one of the 6th, and then we have 373 for our temperature. Okay, so e to the 6th doesn't work for this. So let's do e to the 3rd. So e to the 3rd works. So it says that when the vapor pressure is 91 e to the 3rd and the temperature is 373, the area above the curve is going to be 900. Area under the curve is going to be 9,154, and the area above the curve is going to be 9,143. And this is pretty close to what that matching areas are. So thank you.